Welcome back and welcome to Organic Chemistry 2. We're going to start out with Chapter 12, which is synthesis. And we're going to look at different ways that we can put molecules together. In this image that you see here, this is kind of a cartoon of a pharmaceutical drug that has been developed using multi-step syntheses. When we're looking at solving one-step syntheses, you want to analyze the structures of the reactant and the product. Look at how the functional groups have changed from one to the other. In this reaction here, below, we see that it has gone from an alkene to an alkyl halide. Then you want to think about what reactions and mechanisms you know in order to determine the reagents and conditions. And then lastly, check your answer by working out the mechanism. In this particular problem, we want to make observations as to what is happening. So we saw that an alkene went to alkyl halide. And you might think about HBr doing this reaction. But if you recall, HBr would put the bromine at the Markovnikov position, and it needs to go to the Anti-Markovnikov. So we want to do HBr and add the peroxide to get it to go to the other sender. Synthesis is a pathway towards a product leading from a starting material. This can be a one-step process, or it can be several steps. So we're going from compound A with many steps to compound X. So we might start with benzene and end up with some pharmaceutical drug. We often use retrosynthesis, which is a plan to build things backwards from the product stepwise towards the starting material. Retrosynthesis is a very powerful tool when you know many of the organic reactions. So at the end of 225, you could do a fair amount of reactions. What you'll see in 326 is that we can do some of the same reactions, but in fewer steps, and that will be a much more efficient synthesis. In using a retrosynthesis, we start with compound X, and we work backwards in many steps, all the way to compound A. So just a quick refresher of what kinds of mechanism arrows that we will see. The first one here, we have a nucleophile attacking an electrophile or giving it a hug. So this is the nucleophilic attack, or the hug. In this reaction over here, the bromine is leaving behind a carbocation. So this is loss of leaving group. And this reaction here, the electron lone pair from the oxygen is grabbing a hydrogen, which is giving the electrons back to oxygen here. This is a proton transfer. Which we can abbreviate plus minus H, or PT. And in this reaction that we see here, we have a bromine leaving, forming a carbocation. A hydride shifts while the carbocation moves, and then we get an elimination here. So this is a rearrangement. And just a refresher with Bronsted acids and bases, the curved arrows with the mechanism shows the path of electron flow. Electrons move from base to acid, so the base here is picking up the hydrogen. This is the partial negative, and this tends to be the partial positive in those types of arrows. So with the acids and bases, acids are usually accompanied by pKa values. A pKa of a carboxylic acid is around 5. For water is 15.7. And alcohol is 16. And amine is around 40. Alkynes are 25. Alkenes are 44. And alkanes are around 60. So as we increase the S character, so this is SP, SP2, SP3. This is 25% S character. This is 33%. This is 50% S character. So as that S character increases, the electrons are pulled closer together, which makes it more electronegative, and the pKa then drops with that. And when you're looking at acid-base reactions, the pKa, if we're going to look at which side is favored here, pKa of an alkene is around 44. This is the acid here, which is around 60. This is a weaker acid, and equilibrium favors the weaker acid. There's lots of different representations with resonance. If you remember, resonance is a different way to show electron movement by pushing electrons around, usually around pi bonds or if there's carbocations involved. So for this particular resonance structure, if these electrons move here, this would be the resulting resonance structure. We have electrons here on this carbon, which can move in to form this double bond. The electrons that were in the double bond are now on the oxygen. And there are no arrows shown here, but we can draw a resonance with these. Where the electrons in the cyclic structure have just shifted one carbon over. Substitution reactions that we've seen are SN1 reactions and SN2. If you wanted to see a review of those, you can go back to your notes in Chapter 7, where you can review the particulars of each of them. SN2 reactions, you have a nucleophile that attacks the electrophile, and the leaving group leaves, and that's all one step. The product that forms then is the substitution with an inversion of stereochemistry, plus you get the leaving group. In an SN1 reactions, the leaving group has to leave. It gets ionized, and the nucleophile comes in to form the new product with a racemic mixture and the leaving groups. SN2 is one step, SN1 is one step. If we want to do an elimination reaction, you have a strong base such as sodium amide or DBU. These are non-nucleophilic bases that will only act as base, and that will remove the hydrogen that is beta to the leaving group. And form the double bond. This is the Zaitsev product, meaning that it's the most substituted. If you use a bulky base such as T-butoxide, it will grab the most accessible proton and leave your double bond there. This is the Hoffman product. If you have sodium amide and a strong base, this and excess of that, this would be excess, that would lead to the double elimination. So reactions that we've seen that we can use to do hydrohalogenations of alkenes and alkynes include using HX or something like HBr, which will give us the halogen at the Markovnikov position. If we have an alkyne, you can add one equivalent, and that will give you the halogen here, and you maintain the alkene. If you have an alkyne with an excess of HX, you get additions of two X's both to the Markovnikov position. If you are coming to 326 and you haven't had 225 just last semester, we can go through these reactions quickly, and you can look and see how these are organized and put them into your organic chemistry reaction booklet. These reactions here are all functional group transformations, so they would go into that category. These are from Chapter 9. These are from Chapter 10. These are the anti-Markovnikov reactions. So if we add peroxide to both of these reactions with alkenes and alkynes, we get a halogen at the anti-Markovnikov addition, or the less substituted. This is Chapter 9. This is Chapter 10. If we're doing hydration of alkenes and using the Markovnikov addition, we can have addition of water. Just add water with a catalytic amount of acid. There's rearrangement possible. This is an FGT, Chapter 9. We can add mercuric acetate to get the same thing. There's no rearrangement here. This is Chapter 9. And with the alkyne is Chapter 10. This forms the enol first, which will then tautomerize to form the ketone. For hydration of alkenes and alkynes using the Anti-Markovnikov, we can use borane as our reagent to give us the opposite stereochemistry. Get OH on the end here. This is an FGT. Chapter 9. This is Chapter 10. 9-BBN will also form the enol, and that will quickly tautomerize to give us the aldehyde. So BH3THF with peroxide and sodium hydroxide gives us the anti-Markovnikov alcohol. 9-BBN, which has only one hydrogen available, will give us the enol with the alcohol on the end, which will tautomerize to the aldehyde. These are all reduction reactions of alkenes and alkynes. We have hydrogen and platinum. This can also be palladium, nickel, or other metals. That gives us the alkane. With hydrogen, platinum with alkynes, that gives us the alkane as well. We can't stop that reaction. For Lindlers, this will give us the Z double bond, and the ammonia will give us the E double bond. So this is because the hydrogens add on the same side of the metal with the poison, and then the sodium and ammonia works via a radical reaction. This allows the most stable radical intermediate, and that's why it gives us the E. These all fall under the oxidation reactions. The first one, again, is from Chapter 9 with alkenes. If we use ozonolysis with DMS, that will cleave that double bond in half and put an oxygen there. So we end up with this aldehyde and then this formaldehyde here for a terminal one. Ozonolysis with an alkyne will still cleave, but we end up with now 2 carboxylic acids. And because this is symmetrical, they're both the same carboxylic acid. But if it wasn't symmetrical, if you had a different R group here, that would just be the R there. For ozonolysis of a terminal alkyne, we still cleave. You get the carboxylic acid and CO2. For halogenation of alkenes and alkynes, these all fall under the functional group transformation category. The first one is from Chapter 9. If you have an alkene and you add a halogen, that gives you dihalogenation, and these will be trans to each other. So you get the trans dihalogenation reaction, plus you get its enantiomer. If you have one equivalent of this with an alkyne, you get the double bond. These will add trans to each other. With one equivalent, if you have an excess, then you end up with an excess of halogen. It's also from Chapter 10. For a diol addition to alkenes, these are all FGT as well. If you want an anti-addition, you start with a peroxide, which will form an epoxide, and we will get your trans diol. These are all Chapter 9. You can use osmium tetroxide to give you a syn alcohol. So you would get this plus the enantiomer. And the same thing would happen with KMNO4. These first two reactions are functional group transformations via elimination. This is a strong base. We have excess of it, so you can have a vicinal dihalogen or a geminal one where they're on the same carbon, and that will eliminate both of those with the 2 hydrogens available here to form the alkyne, and we do the same thing here. This reaction here is a carbon-carbon bond forming reaction. So the first thing that happens is the sodium amide is a base that will remove this hydrogen on the end here, the one with the pKa of 25. That forms the alkylide. And that is free to then do an SN2 reaction on that. So you form that R group there. So how do you go about approaching a synthesis problem? You want to look at whether or not there's a change in the carbon skeleton, then compare the starting material with the product to see if the carbon skeleton is gaining or if it's losing carbon atoms. If it's gaining atoms, you might need to go through an alkyne. If it's losing atoms, you may need to do an ozonolysis reaction in order to cleave some carbons off, or maybe do an elimination. Is there any change in the identity or location of the functional group? So is one functional group getting converted into another? Does the position change? So are we moving things around? So that's a couple of observations that you can make here. So if we look more closely at this example, is there a change in the carbon skeleton? If I count up the carbons, we have 1 through 5 carbons here, This one adds 7. So we're adding 2 carbons, carbon 6 and 7. Is there any change in the identity or location of the functional group? Well, we're going from an alkyne to an alkene, so that's changing the functional group. The way that this is numbered here, 1, 2, 3, 4, 5, it goes to 1, 2, 3, 4, 5. The location of our functional group is the same, so we don't have to worry about shifting anything. The alkyne was between 4 and 5, alkene is between 4 and 5, so we don't have to worry about a shifting. So is there a change? Yes. Is there a change in location? No. What reagents do we have or know about that will add 2 carbons to a skeleton? The one that we talked about just in the last couple of slides is NaNH2, which creates the alkylide ion. And then we need to add 2 carbons, so CH2CH3, and that should be accompanied by a leaving group. So the acetylide will form here, which can do an SN2 kicking off the bromine to get us the addition of that. Then we want to look at what reagent will convert a triple bond into a trans or E double bond. Because of our stereochemistry here is E, we want a reagent will give us that and not the Z. So we want to use sodium with liquid ammonia. The other thing that you want to do with reactions is to look at the retrosynthetic analysis. I know in 225 many of you wanted to go in the forward direction, but it will be just as helpful for you to go in the backwards direction. If you're trying to go from an alcohol to an alkyne, instead of trying to start going forward in this reaction, you want to focus on the second to last step. So what do we need to have in place here in order to get to an alkyne? So in order to form an alkyne, we know that we can do that using geminal dibromides where they're both on the same, or a vicinal one here where they're both on the different carbons, or you have the geminal dibromide where they're both on the end. These two are not really useful because we only have reactions to put the bromines on the same carbon if we have to go through an alkyne, which we're trying to get to in the first place. So you want to go with the vicinal dibromide. Which we know we can get to using an alkene. So now we're dealing with the alcohol. What reagent can we use to get to the alkene? Which in here, once we have the alkene, we can use something like bromine to get to the dibromide. We use excess NaNH2 with the alkyne here. So this is not a good leaving group. So what we can do is make it a better leaving group by using tosyl chloride and then using your favorite base, DBU, DBN, or NaH. NaNH2 works. And that will give us this alkene, which you can then send through this to get to the desired product. So for your practice problem, propose an efficient synthesis. You're starting with butene, and then you want to end up with this aldehyde. Think about different reactions that will get there. So to start your process, you want to count your carbons. This is 1, 3, 4 carbons. So we're going to need to add 2 carbons. Our functional carbon alkyne went from being, and I know that I can make an alkyne, and it's now at carbon 6. Plus, so if I work on the synthesis backwards, that gets attacked. The only way that I know right now how to make an aldehyde is from an alkyne. I wouldn't want to try to make this so an alkyne with this because the functional group isn't between 3 and 4. If it had been between 3 and 4, then that could be something different. But because the functional group is now on carbon 6, this is probably the best strategy to go about doing that. So if we had this alkyne plus this, we can make this alkyne here, and then backwards from this particular carbon would get us back to this alkene here. So in my forward synthesis, I start with the alkene. I want to put my halogen on the end. So I have 1, 2, 3, 4. I need to use HX. We'll use HBr. And because I want an anti-Markovnikov product, I want to use the peroxide. I'm going to start with the ethyne. I have NaNH2. Then I'll add the halogen that we just made. Once we get that, we can use 9-BBN followed by peroxide, sodium hydroxide, and that will get us our target molecule. So that's one of the ways that you can go about doing these multi-step synthesis.